Hi, my name is Mert Gulcur. I'm one of the early stage researchers from MICROMAN project, and today I'll be presenting my PhD or ESR project based on microneedle production using ultrasonic micromoulding and process fingerprinting. And I work at the University of Bradford Centre for Polymer Micro and Nanotechnology under supervision of Professor Ben Whiteside. This is the structure of my talk. First, I'll introduce you to ultrasonic micromoulding technology. Then I will discuss some of the aspects of our process fingerprint concept, and then I'll present you our experimental results and conclusions. So the goal of this work is to investigate the process suitability of ultrasonic micromoulding for manufacturing of microneedle arrays, which will be used for drug delivery devices. This is actually the heart of the ultrasonic micromoulding technology. Well, basically we have an ultrasonic stack, which you can see here. It is made of a converter, a booster and a sonotrode, and also an ultrasonic generator we have on the right hand side. So this one generates electrical signals, and these are connected to this converter. This device converts the electrical signals into mechanical displacement using piezoelectric effect, and these ultra-fast vibrations are being amplified using this booster here. And with this sonotrode we make contact with our polymer pellets, and the energy transfer will be carried out using this sonotrode and the pellets, and this vibrates at 30 kilohertz, and it's quite fast and energetic. And as you can see from this video, the sonotrode moves down, vibrating and melting the polymer using interfacial friction and viscoelastic heating mechanisms. And we don't use any cartridge heaters or other heating mechanisms to melt the polymer, but we use only ultrasonic vibration to melt our material. This is the overview of the ultrasonic molding process or ultrasonic micromoulding process. We have our sonotrode at a fixed position, and we have our upper mold and bottom mold here, and we also have the polymer pellets inside our sonication chamber, and we have our injection plunger at the bottom, and we compress these polymer pellets with some force against the vibrating sonotrode for melting the material. So as you can see, the polymer pellets are being melted, and we apply some further force, and then we are able to inject the polymer melt into our micromoulding cavity. So there are some advantages and potentials for this technology. It is good for pharmaceutical materials because we have very short residence times, or no residence times at all, because the process usually takes place within 3 or 5 seconds. So the polymer is exposed to elevated temperatures for quite short times as compared to conventional injection molding or micromoulding, where we have a screw and a barrel system, and the polymer melt is exposed to elevated temperatures for hours in some cases. So this is an advantage for pharmaceutical materials where they are quite expensive at times. And another advantage is that different materials can be molded back to back without any purging or contamination effect. One example here we did was this is a polypropylene with carbon black on the left side here, and in the next shot we used the virgin material, and we had no contamination at all. So this could be another advantage for some applications. But there are some issues going on with this process as well, where the shot amount varies because of the shape of the pellets, and this sometimes causes some repeatability issues. So our case study was microneedles, and we use this microneedle mold insert that you see in this image. We have laser machine cavities, which were laser machined at University of Birmingham. We have 6x6 configuration of 36 needles in total, and we have very sharp tips, 3 to 5 microns in tip radius, and we have approximately 930 microns of needle height or cavity depth for these microneedle cavities. Now I'll introduce the process and product fingerprints for our project. Process fingerprints are some certain process features that we could extract from process data. So these could be peak cavity pressures, pressure integrals, or temperature values, or temperature averages, and they might differ from cycle to cycle, and we need to understand why they differ and if there are any relationships between these process features and the final product quality. And as an example here, we used thermal imaging to extract the temperature of the polymer melt during ultrasonic micromolding. And as you can see in this temperature profile, there are some distinct features like peak temperatures and maybe temperature integrals under the area of this curve. So we could extract these information from cycle to cycle and see and try to correlate with our final product quality, which is defined by our product fingerprints or geometric features. So in our case study, this is the average needle height from one microneedle part or one microneedle array. It is the average needle height from 36 needles, which is our product fingerprint, and it could be also defined as the replication degree or needle tip radius but we for simplifying the problem, we use average needle height from one cycle or one part. And at the end of this, we would like to see some correlations between process fingerprints and product fingerprints, and we try to see if there are any meaningful relationships between these process features, inline process data, and product fingerprints, which is the geometric outcome of our products, which could lead us to zero defect micromanufacturing. The methodologic sort of thing for this process fingerprinting is to select, we first select a process condition that yields reasonable part quality, and then we run the experiments and sort of make like a pilot production scenario and make 100 parts. And we also introduce some disturbances like changing the mold temperature and so on. And we monitor the process. We collect all the process data using machine data or encoder and thermal imaging. And also at the end, we analyze the process and product fingerprints for zero defect micromanufacturing. And here are some of the experimental details. We use this 6x6 microneedle insert, mold insert, and then we used an ABS resin as our material, polymer material. And in the first 50 cycles, we used 80 degrees of mold temperature, and in the second 50, we increased it to 90 degrees Celsius. And we used a sonication time of 3.5 seconds, and we have set a shot size of 270 milligrams. And all of these experimental parameters or values resulted in reasonable part quality, which will allow us to see how the process fingerprinting will work in the first place. And this is an example how we extract process fingerprints from thermal imaging. This is a thermal image taken from the ultrasonic micromolding cavity, and as you can see, we have different regions of interest, and this is, for example, a square region of interest that has been put on this 6x6 microneedle array. And we are also interested in temperature distributions near the gate and near towards the end of the cavity. And we also extract these temperatures as temperature curves, which you can see on the right hand side. These are the average or mean temperatures from these within those regions of interest, and today we will be focusing on the blue curve and the black curve, which are the temperatures from the end of the cavity and from the 6x6 microneedle array. And from these two curves we extract peak temperatures and temperature integrals, which is the area under the curve from these curves, and these are process fingerprints from thermal imaging. And this is how the ultrasonic micromoulding is being carried out, and we capture all the temperatures from pixels at 100 Hertz. If I can play this again, it will be better seen. We also capture machine data from the ultrasonic micromoulding machine, and in this case we have the power output of the ultrasonic generator and versus time on the x-axis, and we calculate sonication energy for each cycle. So basically, if we integrate this curve, it will give us a number in units of joule, which is the sonication energy consumed by the generator for doing making one part, and we calculate it for each cycle, and we use this as a fingerprint for further analysis. After manufacturing our parts, we cut them and use this telecentric optical measurement apparatus for quality inspection. So we use a 5x objective lens on the left hand side here, and we have X and Y movement stages which could move automatically and which could be controlled by LabVIEW based software. And we have an LED light source on the right hand side, which is a telecentric illuminator, and 36 needles can be inspected in approximately 2 minutes, and it's a very useful tool for assessing the micro replication quality of our parts. And this is a telecentric image of the microneedles, as you can see on the top right. So after manufacturing and quality inspection of the parts, we have our process data, and we will write some LabVIEW scripts for extracting process fingerprints like integral values and peak values, peak temperatures, and things like these. And then we plot correlation plots, scatter plots for seeing if there is any relationships between our process fingerprints and product fingerprints. So in that case, we have temperature process fingerprints taken from thermal imaging. We have integral values from the 6x6 array and towards the end of the cavity, and also we have peak temperatures from regions of interest from 6x6 array and towards the end of the cavity. And as you can see, these scattered data gives us very good linear relationships between the average needle height, which is on the y-axis, and our product fingerprint on the x-axis. So we could say that integral values are quite good process fingerprints that could tell us about the microreplication quality of our microneedles. And these R-squared values are quite good, and this represents the goodness of this linear fit to this scattered data, and 0.9 values of R-squared values are quite good for a linear fit, and we have seen strong correlations for both fingerprints. Less so for peak temperatures, but it is still a reason that there's still a strong correlation between the peak temperatures from the 6x6 array and towards the end of the cavity. And The reason for this is that peak temperatures are usually one specific temperatures from one specific point from the regions of interest, and they are usually localized, and they don't represent the part quality as good as the integral values. And integral values are directly proportional to the energy input to the system and viscosity of the material, and so that we have very good correlations for integral values, as you can see here. Another significant result from our experiments was the relationship or correlations between the sonication energy and our microneedle height from each part, and we have seen R² values of approximately 0.7 for sonication energy that is taken from the machine. And this could be quite significant because monitoring this process fingerprint needs no additional layer of instrumentation for inline monitoring, no thermal cameras or pressure transducers or any additional equipment or apparatus. So this sonication energy fingerprint could be a useful and cost-effective method for predicting or doing inline quality inspection of the microneedles, and this could be considered as a good result. I will conclude my presentation and mention some of the future work that we plan to do. We've presented some strong correlations between process and product fingerprints. We selected some process fingerprints and extracted them that will allow us to set quality thresholds for micromolded parts, and we generate huge amounts of data, and these could have further implications, and we are trying to analyze them in more depth. And also we will, in the future, we will be introducing a new nano fingerprint feature that will be used for quality inspection using diffractive methods. I would like to thank European Commission for the funding of MICROMAN, and I thank my colleagues at Polymer IRC and MICROMAN project, and my supervisors, Professor Ben Whiteside, Professor Tim Goff and Dr. Elaine Brown. And thank you very much for listening to this presentation. Thank you.